I welcome you all to today's Biostatistics Session 3. This is our last session in the Biostatistics series. So today we have with us Dr. Sabyasachi Sengupta sir. He is an ophthalmologist and he is the founder and director of Sengupta's Research Academy. He is the current associate editor of the Indian Journal of Ophthalmology, a very well-known journal. He was the recipient of Dr. G. Venkataswamy Gold Medal in DNB Ophthalmology exam held in December 2009. He was awarded the Best Research Fellow as well as Best Outgoing Fellow 2010 to 2012 at Sanskara Netralaya. He was awarded the Young Achievers Award by the Vidarbha Ophthalmic Society in 2015 for his outstanding achievements and contribution to ophthalmic research in India. He has published about 79 articles in peer-reviewed journals and presented more than 25 papers and posters in national and international conferences. Postdoctoral research fellowship at Wilmer Eye Institute, Johns Hopkins University School of Medicine, funded by Johns Hopkins Medicine. His biostatistics course on statistical methods in public health from Johns Hopkins Bloomberg School of Public Health, funded by Johns Hopkins Medicine. We welcome you, sir. There are many more points to your CV, and it's never ending. And we are really inspired, and we feel very blessed to have you here with us today for guiding us on the topic of biostatistics. So you can take on from here.
Thank you so much. Can you introduce yourself as well?
Yes,
so Go ahead.
Okay. So, hi everyone, I am Manali Raut. I am the Research Secretary for the Research Council and the Student Council 2019-2020, and I'll be the moderator for today's session. So, if any one of you have any doubts regarding anything about today's session, you can contact me. Also put it up in the chat and I'll be coordinating it too, sir.
Thanks, Manali, for the very nice introduction, and I thank Neil also for giving me this opportunity to come and interact with all of you. And today's technology is so advanced that we can be in different parts of the world and still connect on a call like this. First of all, I want to say that this is a mighty great initiative that you people have taken, and I know it takes a lot of effort to get this going, but I can only wish that 20 years back when I had joined medicine, that something like this was there, but alas, nothing like that was. But now I think with a lot of this technology and also the desire that all of you are showing, I think you can really go, you can really do wonders. And it's always the motto has been catch them early. So if you understand the importance of this and of essentially of doing research and creating evidence-based medicine, you must be hearing about this term on and off. That evidence-based medicine, etc. Just a second. So you must be hearing about this term evidence-based medicines. What it really means is that you do some good work and you publish papers, and then you essentially learn how to treat people in the right way. And a lot of the times, all of this data is coming from the West, and we are in a developing world where 90% of the population lives. But 90% of the papers and the treatment patterns and whatever you read in your books are all coming from the Western world, isn't it? So there is a lot of disconnect between what is happening in the West and what we treat as. So the onus is really on us to do good research and publish papers so that we can treat our own patients the way it works best for ourselves. Another point before we start on biostatistics is that a lot of physicians, when you go out in the real world, you'll see they'll say, "Oh, there's no need to know any research techniques. That's simply for academics in government institutions and all who want to publish papers." That unfortunately is very far away from the truth. That's because when you are in practice, you are talking to a patient face to face. is something wrong, or am I audible to all of you? Manali, if you can just confirm.
Yes, sir, you're audible.
Yes,
Okay. And you can see me as well, right?
you're audible, sir.
Okay. I hope you can see me as well. And okay. So so a lot of people think that all of this is not really for us or not really for me. But when you're sitting right, face to face with one patient, it's always one on one. The patient expects you to at least offer him all the treatment options that are available, and a lot of the times make a decision for him. So they'll say, "Aap hi bataiye, doctor, which is the best one? Which should I go for?" And then they will go for that. So how do you make that decision? It really all depends on how you interpret what is published in these journals and how you actually take it to your clinics. So for this, it's very, very essential that you understand nuances of published literature. I don't know whether you looked at PubMed search and other things, but when a paper is published, you need to understand whether it's good enough for me to take it to my patients, or is it not. So a lot of these research techniques will very much help you in that. And finally, before I start, I just wanted to say that you have to unlearn and relearn a lot of things that you're learning now. Technology is really galloping at a very, very fast pace. And so what you're learning in your textbooks now and in your post graduations later will likely be outdated in 4 or 5 years time. So unlearning and then relearning happens only when you are able to interpret medical literature. So with that short introduction and a congratulatory note that you are taking this up in a very big way, I'm really happy that you're doing that. I will start on today's topic.
Thank you so much, sir. Just one request to everyone. Please keep your audios as well as videos off. And also don't press on something like start presenting, because then it will disturb the sequence. Thank you.
Right. Okay, so I'm going to start. Okay, so I hope you are able to see my slide. And can you just confirm, one of you? Manali, can you just tell me whether
Yes,
you are
sir.
able to see that?
Yes, sir, we can see.
Okay, so what we're going to talk about today is how do you interact with a biostatistician, and what is the importance of all this. And this is sort of to cap up or to round up everything that you've already learned in your previous sessions on biostatistics. So we'll talk about a little bit about recapping what you have already done, and then take it forward to how to actually take all of this learning to a biostatistician, and then how do you get the best data out of that. So just to introduce you, statistics is basically the science of collecting. It's very simple, it's not really complicated as people make it out to be. So statistics is the science of collecting data, describing data, analyzing data, interpreting and drawing conclusions from data, and then predicting future events, isn't it? So this is the sequence that you go through, and this is what you want to actually get. And finally, we all want to actually be the the astrologer and say, I said this pandemic was going to come one day, So believe me, people have actually predicted this pandemic, including Bill Gates. So these things really work. So statistics really helps you predict a lot of future events, treatment outcomes, surgical failure, etc. So this is important to understand. So statistics really helps us organize, understand, and make sense of all the data that you have. And what really data means is that it's observations that come from an experiment or research. So if you are doing a particular study, then you're going to have certain variables that are, certain parameters or metrics that you're going to get. So that is essentially what we mean by data. And then even breaking it down further, what a variable really means is that it's a set of observations in the data set, or in your Excel sheet. Every column, I don't know whether you've looked at Excel sheets or as yet or not, but then you will soon get to that as and when you start doing your research. And you need to get all your data in one place, so that it's the easiest way is to make an Excel sheet. So every column, so every row will be data about individual patients. So one row is equal to one patient. So if you have 100 rows, it will be data from 100 patients. But there will be so much data from each patient. So there will be, say, 20 points or 21 points or 20, say sometimes 1,000 points from each patient at different visits that you're collecting. So that is going to be your column, and every column is a variable. For example, it is age, gender, say number of injections that you have given. So this is what is data. So we are essentially talking about how to communicate with a statistician, right? So there are some prerequisites which you've already gone through in your previous lectures, but so you need to know what variables are, right? I just told you what they are. then you need to know how to make a good Excel sheet that can be imported easily into a statistical software. So what we do after you send the Excel to a statistician is that we import all that data into a new software. There are different softwares. I use one which is called Stata, Stata. You can Google it up as well. Commonly, people use SPSS, and there is a very sophisticated one which is called SAS, that is SAS. Right. So this Excel sheet should be compatible with utilization in that software. Just to give you an example, an Excel sheet cannot or should not have any alphabets at all in the whole Excel sheet except for the top row. That's the only one row on top where you're labeling your variable, where you say age or you say gender or you say vision or you say blood pressure. That's the only row that should have an alphabet. All other rows cannot have any alphabets. So that is there is one rule, but then many other rules like that. Then you need to know the test of significance, what test to use when. I'll give a quick recap of that as well, but I'm sure you've gone through all of those in your previous lectures. Then you need to define your outcome measure well. What are you exactly studying? Somebody say, oh, we'll study, surgery success hua ya nahi hua, or we'll just say, oh, I gave him this medicine and is he happy or not? But then how will you measure is he happy or not? Are you going to use a questionnaire? Are you going to ask him some goal-directed questions? Are you going to ask him 1 question, 5 questions, 10 questions? Based on that, how will you, finally conclude? Because you just need to know, is he happy, yes or no, right? So you need to define it really well. Then you need to read previous literature and understand the lacuna in existing literature. So already there will be, a bunch of papers which are already published on that particular topic. You need to read some of them and understand what has been done and then what has not been done. So you really need to do what has not been done, isn't it? Otherwise, what's the point of doing it all over again? So understand what has not been done and try to, divert all your goals, including, your writings, your statistics, your tables, your figures, everything should be directed towards filling that lacuna. And then do not manipulate your data or, commit any misconduct, because, it's relatively easy for expert reviewers, or journals to catch that, or, your peers will easily sometimes point out and write a letter, and then people are nowadays it's easy to carry out public shaming, so people may write bad stuff, etc. So do not put yourself in that position. Do not manipulate your data, and it's the biggest form of scientific misconduct if you sort of forge your data. So just keep away from that. So some basic terminologies before we go to our statistician. So a variable can be either a continuous or a categorical variable, or it could be an independent or a dependent variable. I am sure you've seen a little bit about these. So continuous variable basically means it has a unit. First thing is it has a unit to it. So it could be in centimeters or in millimeters of mercury, or in any other so age is like in years. So that is again a continuous variable. So continuous variable has a unit and it can take a value anywhere between 0 to infinity. Essentially, so somebody can actually be 120, 125 years old, like that. So a continuous variable is that, and a categorical variable is it's in categories. So it's like gender, so male and female. It could only be 2 categories. For example, surgical success, it could be a success or a failure, or partial success or something like that. So it could only be 2 or 3 categories. Sometimes there are 5 or 6 categories, but there can't be like 100 categories, right? So you need to understand whether it is a continuous or categorical variable, and a categorical usually either binomial, ordinal, or multinomial. Where binomial means only 2 categories. Ordinal means more than 2 categories, but it has an order to it. So, say good, better, best, something like that. And a multinomial is it's more than 2, but there is no order to it. So these are the basic types of variables. Again in examples. So I need you to think a little bit about, whether height in inches, whether that is a continuous or a categorical variable. So if you quickly think in your mind, it's going to be in inches. So it could be anywhere between A to B, where the P could be anywhere. It could be a very light, somebody very tall or somebody very short. So height in inches, it could be from 0 to infinity, and it has a unit. So it is a continuous variable. Blood pressure in millimeters of mercury. So if you look at systolic pressure, it could vary anywhere between potentially anywhere between say 90 and anywhere between 240, 250, 300. So the blood pressure can vary between a very large interval, and it has a unit, that is millimeters of mercury. So it is a continuous variable. Now gender could be either male or female, or say I don't want to say, or whatever. So could be only 2 or maybe 3 categories. So this is a categorical variable. again, hemoglobin in gram percent. So, say you're doing a study on anemia and some supplements which improve hemoglobin. So, hemoglobin in gram percent is a continuous variable because it could vary really between 2, 3 to 16, 17, 18, and it has a unit to it. But if you say, hemoglobin improved, yes or no, and I want to say, if more than 10 it's improved and it's less than 10 it is not improved. So, it just, you ask the question, has hemoglobin improved? If you say yes, or you can say no, so that then becomes a categorical variable. So a continuous variable can be categorized. I don't know whether I'm confusing you, but it's relatively easy to understand. Again, surgical success, it could either be yes or a no. Recently I've heard a lot of things about HCQ and hydroxychloroquine, and it leads to QT prolongation on the ECG. So QT prolongation due to HCQ, it's a yes or a no. Did QT prolongation happen in this patient? You'll say it could be a yes or a no. Other way of asking the same thing is how much QT prolongation happened. So you say 10 milliseconds or 15 milliseconds or 20 milliseconds or whatever. So that now becomes a continuous variable, right? So it's important to define this well before you start. And then continuous variables are presented as means with standard deviation or medians with interquartile range, or they are best shown as box and whisker plots in a diagrammatic fashion. And though it's not possible for us to go through all of these in a very short period of time, but this is how you do it. And then categorical variables are expressed as proportions or percentages. So you say n comma whatever percent. So you say surgical success was seen in 16 out of 20 patients, and then you say 80% at success, something like that. And bar diagrams are the best way to show categorical variables. And then, differences between variables, I'm sure this is something that you've seen, and I have shared a ebook on this where, I've given some tabular representations of these, but, so you need to understand these so that you can actually tell your statistician, no, I want, this comparison between this and this using this test, most likely. So, so you can, when you are looking at differences between, say, age, and there are two groups, say, you've given drug A to one group and drug B to the other group, and you want to see if there is any difference in the age between these two groups. You use different kind of tests. So if that difference is in continuous variables that we've already seen, you use the student T test or the Wilcoxon rank sum test based on the normality of distribution. And if it's a categorical variable, then you use the chi-square or the Fisher exact test. I'm assuming that you've gone through all of these in your previous lectures, so this is sort of a recap. Now, what we essentially started with is talking, about how to communicate all of this to a statistician. So let's remember that a statistician is not a clinician, and hence he or she is not well versed with clinical terminology. So they really don't understand, what is happening. So for example, if you say hemoglobin has improved or hemoglobin has progressed from say 8 to 11, and so that is a good thing. So the statistician will say, okay, so this is a good thing. But if you look at something like glaucoma, which is an eye disease, and you say this X parameter has progressed or glaucoma disease has progressed, that really means bad. That's bad for the patient, and it's a negative sort of outcome. But then statistician does not understand these things, so we need to be very specific about what each and every column in your in your Excel is telling. So you need to explain very clearly. Clinicians do not do don't do statistics and find it very hard to interact with statisticians and interpret results. So you may not sort of understand this now because you're still in the initiation phase. But as you can ask your professors, it's or PG students who are doing their thesis, you'll realize that this is quite a big pain where the student gives his Excel sheet but doesn't really know what to tell the statistician. And then statistician doesn't really understand what is in that Excel sheet, what was the purpose of the study and what is happening. And then he will send something back, and the student won't really know how to interpret it. So all this is quite a difficult thing to do. That's why this lecture of how do you communicate with them properly. So there's a very large gap that needs to be plugged. So statistician will come in at very many different levels in your study. First and foremost is defining the study questions. Like we talked about the outcome measure, right? So they will help you actually zoom down on that outcome measure because it has to be quantifiable or it has to be measurable. Then they will help you with study design and interpretation of previous literature. They will help you in sample size calculation and hypothesis testing. We'll take a little more deeper look into that. Then they'll also help you with data maintenance and cleaning, designing a blank Excel sheet for you to enter your data in. Then they can help you, of course, with this is their main job, but this data analysis and interpretation of your own findings, and then making graphs and figures that best represent your data. So this is overall. So you can understand that the statistician should come in right at the beginning of the study, not really after you've collected data or that you really want. Okay, I want this result, so please make this for me. But that sometimes can be a bit late, because if you had a wrong study design or you've had a wrong sample size, you can't undo that, right? So you need the statistician to come in even before you start. So first thing, like we said, is that the study design. So what the statistician will like to know from you is what is the rationale for that study, right? Why you want to do this study. Then the various variables and tools for data collection. So you're going to use a BP curve which is manual or a BP curve which is automated. There can be errors there. So they want to know how you are actually measuring each and everything, right? So if you are measuring a pupil size or pupil reaction, are you just going to do it with a torch, or are you going to do it with a particular machine? So there are machines for measuring anything throughout the body. So exactly what and how you're going to do. So that's what they would like to know. Then what is the exposure and the treatment? So basically what is your intervention here? Or what is the tool that you're using for that particular outcome, right? So, it could be a surgical procedure, it could be a medicine, a drug, it could be a questionnaire or anything like that. Then the next is the outcome that you want to study. So we've already talked about that outcome. So you need to define it well, and you need to say whether this is a continuous or a categorical variable, and then, that defining well, say, encompasses this whole slide. Then, of course, if there is any funding support, and you will have to decide what is feasible in your context. So study designs can be many different. So it could be prospective, better than retrospective in most instances. Just a second. Just a second, I'm getting some other messages. Yeah. So, so they will want to know about, all of these, and then you have to decide what is, important and what is feasible in your context, because, there will be a different study design, 2 or 3 different study designs for your own sort of setting. But then, sometimes it's difficult to do a randomized trial, with a very large sample. So you need to understand what you can and cannot do in your own setting. So the statistician will help you, sort of curate the study design based on your needs and what is possible in your center. Then it's important to remember this mnemonic, which is called the PICO approach for study design, where P stands for participants, I stands for intervention, C stands for comparison group, and O stands for outcome measure, where participants essentially means inclusion and exclusion criteria. Intervention means what you are exactly wanting to do. C, that is a comparison group, whether you want to have a comparison group or not. This is important to always consider in any case, in any study that you're doing, because without a comparison group, you will not know how good your new approaches or your new surgical technique is. So, and you can't undo this again in the future. So think about whether you want a comparison group for every study, and then again this outcome measures, that how you want to define. Then sample size calculation, just a second. Yes, so sample size calculation, why is it so important? And you're able to see my slide, right? Because there is some disturbance at my end. Manali, if you are able to tell me.
Yes, sir, we can see you. It's just that there are some audio problems in between. Like you're not clear in some
Yeah.
part. Like it's breaking. So
Exactly. Because I am also getting maybe somebody else is clicking present or mic is on or something. I don't really know, but there are some disturbances in between.
okay, sir. We'll see to that.
No, that's okay, right? I mean, you're getting the gist of the whole thing, right?
Yes, sir. We can hear you.
Okay. So, then next we come to sample size. Of course, statistician will help you with that, but why is it so important, and how and what does it influence in your study? So why it is very important is because because when you're doing a study, then for example, you say drug A is better than drug B. You want it to be applicable to all patients, not only in your setting but in your whole country, possibly in the whole world. So you want to really prove that in the most accurate way, or you want to get to the truth of whether drug A is really better than drug B. Now you can't really go out and study everybody in the population, right? You can't really study a million people. If you could do that, that would have been great. But then you can't really do that. So you need to have a representative sample of that disease process or that population, and then do the study. And once you have conclusions from that representative population, then you will say, okay, so in this, in this group, this drug A is better than drug B. Now it should be the same, when I apply it to all the other people. But that generalized application depends upon whether you have taken the right sample or not. Not only in terms of quantity, but also in terms of quality, right? So your inclusion, we have looked at this coronal study from, from the Ramdev group. I don't know whether you've heard about this. There is a lot of hoopla on that. But if you look at some of their inclusion criteria, they're really poor. They haven't included anybody who's less than more than 60, and they haven't included a lot of comorbidities and many other things. So a lot of that drug is then not really applicable to people more than 60, and then people who have comorbidities. But they are the ones who really need some intervention in COVID-19. So if you do a study like that, then it's not possible to apply it in a generalized fashion to others. So choose your sample inclusion and exclusion well, and also your size should be adequate enough so that you can apply your outcomes or your conclusions to the whole population. So that's the whole. You want to really get to the bottom of the truth, not just have a overview of the whole thing. So that is why sample size is important. And what it influences is, it influences whether the differences between group A and group B that you're studying come out to be statistically significant or not. We'll see a little bit of examples on that. So a wrong sample size will lead to errors, and then when people actually do or give that drug in the real world, they'll say, oh, this is not working, this is not as better as you said it was. So that should not happen. So that's how it influences. So the sample size calculation really depends upon the primary outcome measure that you're studying, and think whether it's a continuous or a categorical variable. It also depends upon what groups are involved in your study, 1 group, 2 groups, or 3 groups, etc. And what are the differences expected in these groups. I'll just give you a quick example. So this table, I can share this later with you as well. But so if you see the top row, just concentrate on the top row, it says the outcome measure. Then it says the comparison group. We saw that C in the PICO group. So the C means comparison group, whether it's there or not there. Then previous data available, whether any previous similar study has been done or not. Then what is the difference? Differences between these groups. What are the expected differences that you think might happen? And then what are the probable differences, or what are the expected differences if there is no previous study like that. So if it's a continuous variable and there is a comparison group, and then there is previous data available on this, then what you have to give the statistician is the mean and standard deviation between groups. I'll give you an example. Say there is a drug A and drug B. You are looking at improving the hemoglobin levels of a certain of patients. Now and the drug A is the old drug and drug B is a new drug. Now drug A we know improves hemoglobin, say, from 8 to 11 gram percent. So by 3 grams it improves hemoglobin by about that much after, say, taking it for a month. And in drug B, from a previous smaller study, we know that it improves it by, say, 4 milligrams. So drug A improves it by 3 grams and drug B improves it by 4 grams. Now this is the information that a statistician wants from you. So he will, the mean and the standard deviation. We just talked about the mean. So say it is 3 plus or minus 2 and the other one is 4 plus or minus 2. So when you give him the mean and standard deviation between these groups, he will give you a sample size adequate for that study. If there is a comparison group but there is no previous data available, say a previous pilot study or something has not been done. So it's always important to give data or give means in one group and tell what is the clinically meaningful difference in the other group. So you say, see, I know that drug A improves it from 8 to 11, but I don't know about drug B, but I would be happy if it improves it from 8 to 12. You can tell them that. So, at least 1 gram percent improvement would be preferable to make it clinically meaningful. So based on that, they can give you a sample size calculation. Then a categorical variable, like, it's like a yes or a no. So a comparison group which is there and then a previous data which is available, what you can do is, difference in percentages of the outcome between groups. So, so here it is, the example would be, group A improves hemoglobin by, say, 50%. Now, how much improvement can happen in drug B? That could you say it is about 60%. So now, based on this information, he will give you samples, right? And then lastly, if it's a categorical variable and there is a comparison group, but there is no previous data available, then again use a pilot data or give percentages in one group and tell what is clinical meaningful. So you say, drug A will improve hemoglobin in 50% patients, and I would be happy if drug B improves it in 60% patients, something like that. So it could be based on a pilot study, or it could be based on what you think is clinically meaningful. So based on this, the statistician will give you a sample size calculation. So, so you will see that, without a comparison group or a pilot study data, it's very difficult to calculate sample size, right? So we'll go back to the previous slide. If you see the second and the third columns, so it says comparison group, it always is yes, isn't it? So there is nothing like there is no comparison group. So without a comparison group, it's very hard to get sample size, right? And you can use concepts of these are some other things that you may or may not. So a statistician may know, but there is concept of disagreement between true and observed discordance. So I don't want to go really into a lot of details here, but remember that if you don't have a comparison group, it's quite hard to calculate these differences or the sample sizes. Then something called hypothesis testing. Why sample size is important? Like I said, it will influence the whole outcomes of your study. So here we need to understand something called hypothesis and null hypothesis. Have you heard about this in your previous lectures? If anybody can tell me, that we don't repeat. If you can.
We learned about the hypothesis testing part in 24th lecture, like
Right.
Srikanth's lecture. He taught us about the null hypothesis and alternate hypothesis.
Right. So you have a little bit of idea about what these are. Yes, I'll tell you what these are in terms of errors in sample size. So type 1 error is when you're rejecting the null hypothesis and accepting the alternate when the null is true. Right. So that really means, so this is a false positive. So that really, the real truth or the ground truth is that there is no difference between drugs. Drug and drug B is the same, but then there is no difference between the drugs. But your study says there is a difference, and your statistics also say there is a difference. So there is erroneously you're rejecting the null, right? So here actually there is no difference, but your study and your statistics is saying there is a difference, right? So you say, remdesivir is good to cure corona patients, but actually it is not good. In reality, it is not good. So that is not a good thing to do. So just a second. So this is the problem with doing it on a phone, where you are going to get a lot of disturbance.
So you can again try joining in from your laptop right now also. You could just
It will be quite difficult now. Now we are into this. Okay. Okay, so we were talking about the type 1 error. Type 1 error basically is a false positive where actually there is no difference. I mean, drug A is not really better than drug B. And if you use it in a lot of patients, you will find that it is not working. But then that previous study said it is good, it is working. And why should that be? So that is an example of a type 1 error. Now we'll see why it is related to sample size. Type 2 error basically is the opposite, where failing to reject the null hypothesis when difference exists between the groups. So it's a false negative. That means in reality, the truth is that there is a difference. And drug A is better than drug B. But the study says there is no difference, and the statistics also say that there is no difference. Right? So actually, drug A is better than drug B, but you are not able to find that statistically significant difference is not coming out. Right? So type 1 error happens when the sample size is too large. So any small difference will come out to be significant. And type 2 error happens when sample size is too small. When it is too small, then actually clinically meaningful or relevant differences will not come out to be statistically significant. You will get p-values of more than 0.05 all the time. So this is how sample sizes influence these p-values and these interpretations. So you will say, drug A is not better than drug B in this case. So which type of error do you think is better to make? Type 1 error is there is no difference, but you are telling there is a difference. And type 2 error is there is a difference, but you are saying that there is no difference. So if you sort of think about this, you will know that type 2 error is a better of the, it's a lesser evil. That's because, you may say that there is no difference. Somebody else may go ahead and do a better study and say that there actually is a difference, right? So it is always better to err on this side. Whereas on the other side, type 1 error, it says that actually, what it really says is that, that there is a difference, but actually there is no difference there, right? So people will start using the drug and they'll finally say, oh, oops, this doesn't work. So, I think, if you really have to make an error, it is better to make a type 2 error. So also, based on this types of errors, it's, when the expected differences are small between groups. So, you say one improves the hemoglobin by 3 gram percent, the other improves the hemoglobin by 3.5 gram percent. So the difference is 0.5 gram percent, right? So that's a small difference. When you have small differences that you're trying to show, your sample size is going to be large. But then if you are having large, differences, if you are postulating that, one improves the hemoglobin by 3, the other improves the hemoglobin by 6. So that's a very large difference. So there your overall sample will be relatively small. So when you're understanding that all these, the results that you read and the p-values that you see, they're all influenced by the sample size, right? So it's important to understand why the sample size is important and how it influences. So too large a sample leads to type 1 error and too small a sample leads to type 2 error. It's what we have already seen. So there's something else called the power of the study. So I won't really confuse you. You can read about this. So, power of the study is should be at least 80%. That means if you repeat the study 100 times, you should get the same result 80 out of the 100 times. So that is important that your power of the study is about 80%. So, so I already gave you the previous slide was an example of ophthalmology, which may not be easy for you. So, this is so far what you've seen is how the statistician helps you with the study design, then the PICO approach, then your outcome measures, and then your sample size. Then the statistician can help you in data maintenance. So data maintenance is say midway through your study. So you already have some patients, and then you're going to recruit more, but you want to see whether that data coming in is of good quality or not. So you can ask your statistician to design an Excel with the variables and the labels, and then at periodic intervals try and tease out outliers. The outliers basically are extreme values, and see whether they are due to data entry error or real values from a patient. Right. So, for example, it could be that it's a pediatric study, and instead of 10, you have falsely entered it as 100. Just you were sleepy, and that data entry person has entered instead of 10, they have entered 100. Now suddenly that age, the mean age instead of 10 point something becomes very large, right? So then you will start seeing, why this is so. So if you have a very large sample, say 300-400 patients, it becomes difficult to identify this one data entry mistake at the end. Though it can be done, but it's better that on a weekly basis you sort of go through your data and clean that. So a statistician can help you with that as well. Of course, data analysis, that is the main sort of job that we so far know, but then there are other ways in which statistician can help you. So you can ask for specific descriptive and analytic statistics from your statistician. So like I told you, say descriptive statistics mean standard deviations or medians or interquartile ranges. And analytic statistics, like we already have seen a little bit, is differences in terms of, you use a student test or one of these tests and get some analytics like that. Of course, communicate the study idea. If you are coming into a statistician at a later stage, and after everything is over, then you need to communicate the study idea, the outcome measure, and what each column means, how each variable has been labeled, right? And it's called a code book. So you need to actually explain everything to the statistician, and more importantly, what is the expected outcome. So, why did I do this study, and what do I expect out from the study? And then send sample tables of a previous paper and ask statistician to fill out the table. It's a blank table, right? So you'll say, I want comparison between group and group P, group A and group B, and based on these parameters. So you say age, gender, pre-operative blood pressure, then intraoperative, whatever, then post-operative, whatever outcomes that you want to do. So you already make a sort of a skeleton table where there is no data, but the variables that you want, relevant variables are there, and the groups are already mentioned. That helps. That helps them approach that analysis easy way, and then ask them for relevant graphs. Say it's a continuous variable, you should ask them for box and whisker plots so that your data can be shown in the best way. So they should be able to tell you what is the best way to represent your graphs. So overall, so the statistician will help you in defining the study question, the study design and interpretation of literature, sample size calculation, and hypothesis testing. Whether there is an error on one or the other, type 1 or type 2, whether you're erring. Then, data maintenance and cleaning. So they can help you with designing a blank Excel for you to enter data. then they can help you with, of course, data analysis and interpretation, and finally making graphs and figures that best represent your data overall. So this is what your statistician can help you with, and that essentially brings me to the end of my presentation. And I'm going to stop my slide share now. All right, so these are a few things that I wanted to discuss with you. I don't know whether it makes any sense, or or whether it became a little bit too complicated for all of you. But I would love to hear your questions, and we can have a Q&A now. So please go ahead. If one of you can read questions that are there.
Oh, yes, sir. Guys, please put your questions up in the chat box. Sir, could you just elaborate on power of the study? How to power your study?
Exactly. So, see, essentially, your power of the study comes at a later date. Initially, when it's, say, a prospective study, and you are going ahead with calculating a sample size and then recruiting that, and then presenting your data. There, the power of the study, the question does not really arise, because you've already calculated the sample size. The power of the study arises when you have not calculated the sample size. Say, for example, a retrospective study where you're looking back at all that data, or you are looking at reporting a secondary outcome. So say, for example, you said hemoglobin was your primary outcome, but then you also want to report on another paper you want to do, which is on, say, RBC count. Did this drug also lead to an elevation in the RBC count, or let's say some other metric like that? So say serum ferritin or something like that, where it's an iron tablet. Now, if you want to do that, you have not initially designed your study for that outcome, right? You have designed your study for a different outcome. So here you look at a post hoc analysis. Post hoc means you're looking back at your data and trying to find out something which you were not initially looking for. Now you want to see, whether the study is powered enough to find differences in serum ferritin levels, or find differences in this other parameter that I was not planning to calculate before. That is when you want to see the power of the study. So is my study good enough? I know it is good enough to see difference in anemia or hemoglobin percent, but is it good enough to, robust enough? Are the numbers good enough to find out differences in, the RBC count or serum ferritin in a reliable way? So that is when you look at the power of the study. If you see the power is 80% or more, that means it doesn't really matter. So your conclusions will be very reliable. So that is where the power of the study comes.
Okay. Thank you, sir. The next question is, how do we calculate the sample size when comparison group is not available?
Yes, sir. So it should not happen that your comparison group is not available, because comparison group could be anything from a normal population to somebody who has not had the surgery, or somebody having a placebo, or that really depends upon your type of study that you're doing. But so doing a comparison study without a comparison group is not a great idea. That is because it's difficult to calculate sample, and then it is difficult to do a lot of other statistical analysis from that. However, having said that, if you don't have a comparison group, you have only one group, right? Here there is no comparison group. So how are you going to compare age or gender or etc.? So then that statistics really becomes not so easy. So what your statistics is going to then be revolving around is, so I got this outcome. Now, what are the factors which are predicting this outcome, or what are the sort of determinants, or what are the influencers of that outcome? So you say surgical success, and what are the preoperative variables or preoperative characteristics which predict success, right? So that is basically how your statistical analysis will go without a comparison group. And then you have to see that you should get enough number of success, right? So the number of events then become important. But then it's very hard to calculate sample size without a comparison group. There are ways, but it's quite hard to explain it to you. If you want to Google, there is something called discordance rates between populations. So that is something that we use. But essentially, think about always having a comparison group.
Right. So our next question is, why does too large a sample size lead to type 1 error?
Right. So yeah, this is a great question. So like I said, this relationship between the p-value and the sample size and these perceived differences are very fluidic, right? So that's why we need to come at a exact. That's how statistics work. So if it's a very large sample, much larger than what you should be taking, then anything that is very small, a difference of 0.2 gram percent, say, of anemia or hemoglobin, say one improved it by 3, other improved it by 3.2 gram percent, but then it's not really clinically meaningful, right? But statistically it is coming out to be significant. But so that's how it works. So you need to have a real balance between a clinically meaningful outcome and a statistically meaningful outcome, and that's a sample size calculation is very important. But so all differences, very small differences also get inflated when you're looking at the statistics and the p-values there. So what influences that p-value essentially is the sample size, then it is a standard deviation, and only lastly it is a mean, right? So sample size is the one which really influences p-values there, and that's how statistics work. Very small differences will be very amplified when the sample size is too large, and that's why you will get a significantly different p-value there.
Okay, I hope the doubt is cleared. Our next question is, what is the purpose of a pilot study and what are the indications and best methods to do so?
That's a great question. So here when you don't, so you are dealing with something very new. That's the first thing that we should remember is you want to do a pilot. Pilot means a test run, right? We do a test run before going on a Google Meet call or on a Zoom call just to see everything is working well or not. Similarly, you need to do a pilot study to see, whether there is any, whether there is any meaning of doing a larger study. So if you do say a smaller study and you see, oh, there is absolutely no increase in the hemoglobin at all, then what's the point of going ahead? So first thing is that it should be, that we're doing it for something which is very new, where we don't really know what is happening. One. So for something which is, we already have some previous data, we don't do a pilot, right? So pilot is for something which is very new. That is the first and foremost. Second thing is that you want to do a relatively larger study going forward, and you want a comparison, to calculate sample size. So your pilot study will help you calculate the sample size for the larger or the bigger study. So these are all concepts which also come into randomized trials which are divided in phases. So phase 1, phase 2, phase 3. So phase 2 is sort of considered as a pilot for phase 3, where you do your sample size calculation for phase 3 based on results of phase 2. Phase 2 study sample is calculated based on phase 1, where phase 1 is taken as a sample or a pilot. Now phase 1 is based on animal experiments, where it's going back in time, right? So phase 1 is based on pilots from animal studies, so that is taken as a pilot study there, right? So pilot study essentially is to look at what you have, what you don't know. There is no known information, so it's completely new, or you don't know whether it works well. Or second thing is it helps you calculate the sample size for the relatively larger study later on. And so a good number is to do 30 patients for a pilot study. That's essentially what you want to do. So 30 people and then see what is happening. So that is sort of a benchmark number that people agree with. That's how you do a pilot study. You can go ahead with the next.
Okay. So our next question is, how do we know what is the ideal sample size for a study?
Yes, so like I said, you have to base it on previous experiences. So, it could be either pilot data or somebody has, you want to compare, say, two surgical procedures. Now, there has never been a comparison study here. Some people have done their previous procedure and a new group has done a new procedure, but they have really never compared it across, in the same sitting or, something like that. So you want to do this study to compare and see whether actually one is better than the other, because you might be following the older technique, but then some people are describing, oh, this is a new thing, it's great and you should use it. But then is it really better? And then by how much is it better than, how much benefit is it giving to me and my patients? So then you want to do a comparative study there, right? So you use this previous experience and then you calculate the sample size. So that's how you calculate. So how do you know it is the right or wrong sample is based on what previous studies have done and what your statistician is giving you based on previous study. If you don't have previous data, then you use the pilot study.
Right. On what factors does the power of study depend?
Well, power of study is dependent on only one thing, that is the sample size. If the sample size is wrong, then your power of the study will be less than 80%. It could be too large or too small, either way. But your sample, if it's the wrong sample size, the power of the study will be 30%, 40%. If your sample size is right for that outcome, we are looking at, let's remember that every study is funneled into showing whether that one outcome is right or wrong, or true or false, right? So if you're looking at a different outcome now, that's where you are sort of looking back at the data and trying to find out that other outcome, whether it's true or not. That's where you want to do a power calculation. That's called a post hoc analysis. I have a blog on that. If you want, you can actually take a look at post hoc analysis.
Next question. What are the sampling methods that you have experienced to be the most helpful?
Right. So, sampling methods really depend upon the type of the study that you are doing. If it's a, essentially there are two major types of studies. One is a descriptive study, which is more like a survey in where you go to a population and you do that survey. And the second is a sort of an analytic study where you are trying to find out differences, between drugs and surgical techniques, etc. So when you're going out and into the community and doing, so that's a survey. There are many different types of sampling where you can do a randomized sampling or cluster randomized sampling or something like that. And I'm sure you'll read it in your PSM lectures. And in the analytic, again it depends upon whether you're doing a prospective or a retrospective study and whether you're doing a randomized trial, right? So your sampling techniques will be different. Where when it's a retrospective study, your sampling will be all based on what are the case sheets which are available and how much data you can extract from them. If it's a prospective study, it really depends upon how your sample size has been derived and how many people you need. And you will screen that many people, and then you will say, okay, these people, satisfy our inclusion criteria. Let's, try and recruit them for the study. If it's a randomized control trial, then you will, first recruit the patients, and then you will say, oh, you may get drug A or drug B, and that is going to be based on a pure, sort of luck of the draw, or it's a randomized manner. So essentially, sampling techniques depend upon the type of study that you're doing.
Okay, thank you, sir. Our next question is how to avoid biased selection of sample.
Right. So essentially, selection bias can only be only one way of removing that is by randomizing. Right. So I mean, you don't want to give drug A to people who already have a good hemoglobin, and then say, oh, his later hemoglobin became even better. And then you may end up giving drug B to people who have already very low 6, 5 like that. And then, you'll say it improved only to 8. And then you'll say, oh, drug A is better than drug B. That's basically what we mean by, in this ongoing example, that's essentially what we mean by, selection bias there. So that can essentially only be removed by randomizing. So, if you think that is going to have a very large impact on the study, then it's better to go for a randomized control trial. However, sometimes people just get auto-randomized. So when you look at a retrospective study, say already some 100 people have received the drug A and already 100 people have received the drug B. Depending upon say the physician's choice or or whatever there is. So when you start looking back, this is a retrospective study, and you see meaningful. So what essentially you are looking for is, was the baseline hemoglobin the same in both the groups, right? So if the baseline hemoglobin is same in both the groups, the mean and standard deviations is the same with no significant difference in p-value, then they are auto-randomized, right? So a lot of times that can happen as well. So, but sort of only one way to prevent selection bias is by randomizing.
Okay, sir. Our next question is, so what's a multiple logistic regression?
Right. So I haven't introduced a lot of these complicated sort of concepts here. But let me just tell you what is regression, since there is a question here. So what in the beginning of the class we talked about predicting future events, right? So you want to predict surgical success, or you want to predict which patient will benefit from this drug better than others. So we are looking at predictive analysis here. So people use it a lot for market research or for saying, this company's share is going to skyrocket and this company's share is not going to skyrocket. So there are determinants for outcomes in any field. So in medicine, it becomes important because we deal with life and death, or we deal with health. So, but the concepts are the same, where there is an outcome, and you are looking at these 4 or 5 factors which are going to influence that outcome, right? Now, which amongst them is going to have the most heavy influence? If you can identify that, then you can say, baseline hemoglobin is the best predictor of how the final hemoglobin will be, irrespective of the drug, for example. So, how do you find that? So that is by something called regression analysis. So here we are essentially talking about causality association, right? So which factor is going to influence that outcome the most? Now let's remember there could be 3 or 4 different factors, right? Not necessarily only one factor. There could be many factors which will influence that outcome. Now you find that by doing a regression analysis, where you adjust for many different factors. Where you say, what if all patients were of the same age, were of the same gender, were of the same hemoglobin, baseline hemoglobin, and of the same other parameter. Now, still, does drug A behave better than drug B? Given that everything else is the same, does drug A behave better than drug B? Or, is there still a difference between these? Given that everything else is standardized now, that is what we call regression analysis. Logistic regression analysis is one type of that analysis, where the outcome measure is a categorical outcome. So you say success, yes or no. You say, well, did the drug work in improving hemoglobin, yes or no? And the outcomes are in terms of odds ratios. Right? So I have a blog on regression analysis as well as on odds ratios. If you want, you can go and read. It's written in very simple language. So that will hopefully answer more with a lot of easy examples. So you can go and read that, but essentially this is what regression means. Predicting a future event.
Right. Our next question is, what are the types of bias?
Well, there are many types of bias. First and foremost is when you think that a lot of these biases can come in, bias can also mean cheating, right? So it's a part of misconduct as well. So there are lots and lots of different types of biases where I'm sure your PSM textbooks will also tell you, but selection bias is one bias which is very important to take care of when you are actually recruiting a patient. And then observer bias is the other thing, where say the active hemoglobin is 11, but you want that drug A to look better than drug B. So what you say is you enter in the Excel, you enter 13. So from baseline 8 to actual being 11, but because you want to show one drug is better than the other, you actually enter it at 13, right? So if you've done this systematically over a sample of 14 or say a sample of 400, 500 patients, it's very hard to later go back and see that this misconduct has happened, right? So that is observer sort of bias. So this is taken care of by something called masking, where the person who is actually looking at that hemoglobin doesn't really know whether the patient has got drug A or drug B, right? So 3 things in a randomized control trial are important. One is randomization, one is allocation, and one is masking. So randomization takes care of your selection bias. Allocation means seeing to it that patient got the drug, right? So it so happens that patient number 5 is supposed to get drug A, but did he actually receive that drug A, right? So that is called as allocation. And then third is masking. Masking is basically over the whole study, you will the person who is, or we call it the PI or the principal investigator, he will not know which group the patient belongs to. So just remember that if you include all these 3 in your study design, most of your biases are taken care of. Randomization, allocation, and masking.
Okay, sir. Our next question is, what are the most important things to keep in mind while doing research at UG level? Basic, not related to biostatistics, but yeah.
Right. I think first and foremost is you need to find, I think it's important to get a mentor at an early age. So you look at your faculty, and so don't tell this to your faculty, but look at the faculty who are actually doing some meaningful research or who have had some publications in the past. They're more likely to be interested in having you on board and discussing ideas with you and giving you time so that you also learn. So I think that is important, where you will approach somebody who is actually interested in this. If you approach somebody with, it's a study of some department, but then that person doesn't have a lot of interest in doing anything like that, there's no point in approaching that study, right? You can approach maybe a younger lecturer or somebody who actually has done some work and is interested in that. So I think important is whom you approach and then how you approach. So if you have something in mind, you need to have a concrete idea. Okay, so this is already done, but I think this can be done as well. And so basically you do your homework and then approach somebody, right? So when you approach somebody a little above on the hierarchy, you need to understand that you should do your homework and then go. So approach somebody whom you think will be interested in this, find out what has been done and then what has not been done. And then if possible, maybe after the first discussion, you can design the protocol and say, this is what. It could be it could be a retrospective study where you say, okay, so these are I want to go to the medical records department, collect the files, and this is what I want to study. And these are the different parameters I think will be important. So this approach will possibly help you. Whom do you approach? How do you approach? And then how do you go ahead with it? Of course, once you have the data with you, data is a new currency. I don't know whether you've seen Facebook and Google and all of these people. So trust me, this is going to be more and more and more important as we go ahead. People are looking at insurance companies are looking at grading physicians. Patients are looking at whom to go, whom not to go, and banks are looking at whom to fund and whom to give more loans and whom not to give more loans. So all of this is getting tied up as we go ahead. So doing publications gives you a lot of credibility. So think about doing it right from your UG days. Approach somebody whom you think is interested. Design it or think about it more. Just don't go and say, oh, can we do this? No, that is wasting someone's time. So, this is what I have read. This is what I think can be done. Are you interested or should we do it? And then this is how I want to do it. So, I think that approach should help.
Yeah, thank you, sir. Next question is, could you just explain on blinding and its types, reliability and validity?
Yeah, so this is a little bit outside the scope of what we are discussing. We can have a whole sort of session on validity of a study and reliability of a study, but so there are basically two types. One is internal and one is external. So internal is, if you look at your own patients, we are talking about reliability and we are talking about validity, right? So reliability means internally within the same study. So if you would do again the study on the same patients over and over again, would you get the same results? Is what you call by internal. So this is called reliability. And then validity is basically, if you do the study on a different population, will it still be valid? Will you still get the same results? So that is basically what you call by. These are essentially two concepts that you should remember. And can you repeat the first part of the question? I just lost.
So blinding and its types.
Yeah, I don't know whether there are many different types of blinding, but there are many different ways of doing blinding. Or so blinding in ophthalmology, we don't really like to use that word blinding because of obvious connotations with disease. So we like to use the word masking. So it could be the patient is masked alone, it could be the investigator is masked alone, and it could be that both are masked, right? So it is a single blinded versus double blinded versus more blinded or more masked. Now it really depends upon what you think are the who can have more influence on that study. If you think the principal investigator, he is going to have a lot of influence if he that is observer bias, that is definitely going to be a major factor. So the investigator must be masked or must be blinded. So that is single blinded. If you think the patient may also have a outcome, so they may perceive it in a particular way, and then they may also influence the outcome of the study, then you mask them also. So for example, if you are giving them a tablet, you put some sticker or you do something so that they can't see the name or something like that. Or if you're giving them an eye drop, or you can put sort of a sticker around that so that they can't see the name or something like that. So these are the two, and if both are masked, first step should be to mask or blind the principal investigator, because that is most critical. A lot of the times it doesn't make sense to mask the patient because they may not really know what group, and it may not really matter to them in what group they are. And sometimes masking is not possible. For example, you're using two techniques of fracture repair. One is from externally you can see those, one is X kind of fixator and Y, other is the Y kind of fixator. So as soon as you see the patient, you will know, right, which fixator was used or which technique of surgery was used. So there, masking is absolutely not possible. But then, that's how it is, and people will understand when you write. So either mask the investigator alone or mask the patient or mask both of them. I think that should take care of most of these biases.
Yes. So the last question for today. How do we know that there is an error in our study?
Right. So I think that's a really nice question to sort of finish it off and sort of take home message is that, despite calculating sample sizes, despite going through a lot of this rigor, it may so happen that your patients are not behaving in a particular way that some XYZ patient in Europe has behaved. So this calculated sample size is either based on somebody else's data or based on your assumptions, right? Some basic assumptions are there. Say, hemoglobin should increase from 8 to 12, and then in the other group it should increase from 8 to 8 to 11. But then this has not happened, and because of that, because of these basic assumptions, your results are not really coming, and then you are suspecting, oh, everything I did by the book, but then it's not making any sense. When it is clinically meaningful, but it is not statistically significant, or either other ways too. When it is clinically not meaningful, the difference in hemoglobin is not really meaningful, but it is statistically significant. That is when you start doubting that there is a garbage somewhere there, where your sample size has possibly gone wrong. So clinically and statistically, both should go hand in hand. That is essentially when you need statistics, right? If you say, one group dropped BP by 70 millimeters mercury, and the other group dropped BP by only 20 millimeters mercury, then you really don't need any statistics. It's so easy to understand, oh, obviously one drug is way better than the other, right? So from 240 it made it to 150, and then the other group dropped it only to 210. Obviously you will use one drug which is way better than the other. So when it is clinically, the differences are huge, you don't at all need any statistics. But when, one dropped it by 40 and the other dropped it by 50 or 55, that's when you start doubting, and that's when you need the statistical backing, right? So the overall outcome should be statistically and clinically meaningful. Both should be, right? And it should fit into the overall scheme of larger literature, because finally your paper that you write will be published and it will be fitted somewhere in the jigsaw of the existing literature. So everything should sort of fall into place when you are, when you have the results in hand. So that's a good take-home message, where if you think that clinically meaningful, statistically meaningful, or statistically significant difference, clinically significant difference are both going hand in hand, that's when most of the things are in place.
Yes, sir. Sorry, just one last thing.
Yeah.
According to you, what are the challenges in Indian research?
Well, I think that's again a whole advocacy question where there are a huge number of challenges, and so you can go to my website called Sengupta Research Academy, and you can go to the blogs page. The first blog is written by Dr. Atul Ursekar, who is one of the very leading ophthalmologists in Mumbai and practicing at the Slope Hospital in Mumbai, and he has written a beautiful, very very thoughtful, thought-provoking, I should say, blog on what are the challenges facing research in India. And you can follow me on Quora and these other platforms where I sort of answer some of these questions time to time when there is time. But then essentially, I think the first and foremost is that we don't have mentors to follow. So we don't have role models at all. If you look at most of our teachers, seniors, they are all great physicians, they are great surgeons. But then they are all restricted to their own hospital or their own city, right? Most people, a lot of them may not be known outside, and they have not done any research. They have not really sort of concretized their own thought processes, because you may feel that this is how it works, this is the best, but essentially it may not be. So we have great role models who are good at at diagnosing, at reading an ECG or doing a particular complicated surgery, neurosurgery, whatever. but they are poor at research because simply because we that mindset hasn't been there. So we don't have role models. I think that is first and foremost. Second thing is uh, you know it still is clinics more than research because the payback, if you see, is not very high if you want to get into research. But then you should not think about research as something different from clinics, right? It's only going one step beyond to treat your own patients. So you say, oh, this is something that has been written in books I'm treating, but I'm not getting what results I should be. So that gets you thinking, and then you start, and then you do a study, and you say, oh, so this study is important, or this drug is useful only in people who are less than 65 and not more than 65. That is very useful piece of information that your thought process started, and that you have shown the world, right? So it makes a huge impact everywhere. Now, so who you should be adequately rewarded for that, or there are these things which are coming up now where promotions are based on this, and a lot of grants and funding are based on this, but it is slowly coming in, but the amount of rewards which are there are not high. There are many other kind of problems in terms of regulatories, government creating a lot of red tape in pretty much everything that there is to business. Similarly, everything. So if you ask the pharma, why don't you manufacture anything in India? Why do you import everything from China? That's true because pharma in India do not manufacture any active ingredients. So something like API, which is called an active pharmaceutical ingredient, is all imported only from China. They only sort of assemble it in India here. Now, if you ask the pharma, why don't you do it? They say, oh, India is the only place where you need a lot of permissions to do research. There is no R&D which is possible. So there are a lot of red tapes as well. But I think if there is a champion who has overcome these and shown you that it can be done, then we all start believing. So I think if at all we need to have as mentors, at your stage, it's not that what can one person do, what difference can one person make. It's not like that. One person can always start and others will follow. So if you are able to do this, if you are able to show that at undergraduate level I have done say 5 papers, and then at postgraduate level I have done that many papers, and so you start becoming a role model for others, right? So don't think that, oh, I'm just 17 or 18 and that I can't do much. It's not like that. So you should try showing others, and then finally you will become mentors, right? So then you will have people following you. So I think that should be a very important thing that all of you should take this forward, really push it through and do some meaningful research going ahead.
Thank you, sir. Thank you so much. Anyone else wants to say something? Because I think the session is almost done.
Not an issue. I would love to hear some comments if anyone has anything to add or anything. Please introduce yourself and then.
Okay. Should you do you want everyone to introduce themselves?
Well, I would love to interact on a personal basis, but I don't think we have enough time for 50 people to go through that. But if somebody wants to make a quick comment on what you think was good about this lecture, or what you would like to see more, if you have future interactions, that would be nice.
Right. I think there is some.
Also, I have a website which is called Sengupta Research Academy, and there's a lot of material on scientific research and started and how you can build on it. And there are some online courses, there are lots of good blogs, so you can explore whenever you have the time.
Yes, sir.
Hi, sir. This is Neil Kavedia here.
So, hi, Neil.
So we went through your website, and probably this is one of the best websites we've ever come across. Like everything, right from the basics to advanced stuff, it's very well organized, and it helped us a lot. And especially about this session, all our doubts were cleared in a realistic manner, probably which never happened before. So thank you so much, sir. So only one question is that can we collaborate with you in future, like in any other research related to ophthalmology or any stream as
Yes,
well?
I'm always available for what's called in brainstorming, where We really found arguments and found a way at what's this, what's that, why this, why not that, and I'm always open to that. We have exchanged notes at 2 a.m. and 3 a.m. and whatever. So I'm always open to your ideas, and I can show you the way forward. So this is probably the better study design amongst the two that you have, and this is probably the right sample that you're doing. And
Okay.
if you have a statistician, I can tell you, this is the right way of doing a particular statistics for a study. I may not be able to help you with the nitty-gritty, say actually doing the study or writing the paper, but then I could always come in and sort of take a quick overview of what has been done. So that could always be done. I have a whole team sitting, so I have biostatisticians, I have medical writers, so I could mobilize some of those resources, but we could do that.
Okay. Thank you so much, sir. It was
Thank you,
great.
sir. Okay, so I think we can conclude the session now. We really thank you, sir, for taking out your time from your valuable, things that are going on right now, and guiding us on such an important topic in such a easy way. And I also thank all the research council members and all the teams for helping out in organizing this. And of course, a big thank you to Dr. Kinikar ma'am, because she is always there and guiding us through all the events that we conduct. And the last thank you to our lovely audience for bearing with us through the technical issues that we had. So thank you everyone, and I thereby conclude the session. Thank you.
Thank you so much. Bye bye.
Thank you.